Hey class, wanted to go through a couple of proofs from the homework on 1.2. Sorry I didn't get these up yesterday. Proving is something that used to happen a lot in the old linear algebra class when it was 3 credits. They've cut that mainly out. The proofs that we do ask you to do are much easier, and they're fairly algebraic, doing kind of algebraic manipulations. Things that students are more familiar with. The task of proving, I know, is something that's not easy for lots of students. If you want to learn how to prove, take 290, Math 290. It can be an awesome course. I loved 290, especially the first part. Get it from a good teacher, can help you a lot. But I have written down a few things about proving over here. So the proofs we do in this class, since they're going to be very algebraic, you're going to do algebraic steps, where each step has to be justified by something that we already know is true. So that's either the hypothesis for given information. So they might say that like U is orthogonal to V. Like we can start with that because they say that that's the condition we're starting with. Properties of mathematical objects like dot products, theorems, that's anything previously that's already been proven, logic, so we use logic, sometimes it's set theory logic and other things, and definitions. Definitions play a key role in proving things. The proofs that I'm going to do, it's going to be 68A and 68B. Those, they both have to do with showing things are orthogonal. And so you ask yourself, what does it mean for it to be orthogonal? Well, the definition that the book gives for orthogonal is that two vectors, A and B, are orthogonal to each other if and only if A dot B is 0. So if they say something about the two vectors being orthogonal, we're going to have to use that definition about what it means to be orthogonal. Mathematicians are very careful to have precise definitions of what they mean. That's different than what happens in lots of other fields. Ask people what love means, for example, or what understanding means. People have definitions, but they're different and often not precise. So 68A says, prove that if U is orthogonal to both V and W, then U is orthogonal to V plus W. So we have some given information. We know that we do know that U dot V equals 0 and U dot W equals 0. We know that because it's given information. But we need to show, that U dot V plus W equals 0. That's what we need to show because that's a definition of being orthogonal. We need to show that dot product equals 0. So let's start with that dot product. Let's do some algebraic manipulations and see if we can show that it's 0. So let's start with U dot V dot plus W. Well, that equals what? Well, we can distribute this. We can distribute that U across to the V and W because that's a property of dot products. It can be distributed across addition. So then we can rewrite that as U dot V, put a tail on my U's, plus U dot W. Now, we know each of those is 0. Oh, so I should, before I do that, I should say, like, we can do this by the distributive property up above. So u dot v is 0 plus u dot and u dot w is 0, and this is by hypothesis, or you can say by the given information. Because that's what they told us right here. So we knew that was true just by hypothesis. That's what we're assuming. And 0 plus 0 is 0 by arithmetic. Okay, so the arithmetic stuff you don't have to justify, as we're already familiar with it. So by arithmetic. So therefore u is perpendicular or orthogonal to v plus w by definition of orthogonal. Okay, so only like a 2 or 3 line proof, not bad. Next one's a little bit more intense, but it follows the same pattern. So we're going to show, we need to show it's the same hypothesis as above, but we have to show that u is orthogonal to s v plus t w, where s and t are scalars. They're just constants. Okay. So let's start at the same place. We need to show that u dot this thing is 0. So so let's start with u dot s v plus t w. That equals, well, we can do the same distributive thing and distribute out the u. So u dot s v plus u dot t w, and we can do that by the distributive property. And now we have these scalars. What are we going to do with those scalars? We'd like to get a u dot v and a u dot w before, like we did previously, because we know those will be 0 because they told us that they were orthogonal. So, well, let's look back up at our properties, and we can use like the commutative or this one to move that scalar outside. So we could rewrite, oops, I'm just going to do it in one step. So we're going to pull that s out. S times u dot v plus t times u dot w. So this is, I don't know if they call this a property, but so that's by commutative and by scalar. It's really an associativity, but so by scalar associativity or scalar rule. Associativity, however you spell that. Okay, and then that gives us s times 0 plus t times 0. So by hypothesis, and that gives us 0 times 0 plus 0 to 0 by arithmetic. And so then we conclude the same way. Therefore, U is orthogonal to S V plus TW by definition of orthogonal. So there you go. Hope that helps with the proofs and the kind of proofs that we'll be doing. Very algebraic and justifying by the moves. So thanks.